This will be a presentation on Newton's laws of motion, and we're only going to be looking at the slides for a short time, just to give a few kind of pictures of Newton and a tiny bit of biography of him. I had a student who looked at this picture of him one time and thought, Newton looks like Robert Plant. I don't know if you know who Robert Plant is or not. He was the lead singer of Led Zeppelin. He's still around. He's aged. But this is what Robert Plant looked like as a fairly young man during the 1970s, and he does look a little bit like Isaac Newton. So here's a portrait that was done of Newton. They were big on wigs in those days. He was born in, actually the year he was born, it was 1642. He was born on Christmas Day of 1642. But after that time, and I think it wasn't even during his lifetime, Britain made the switch from the Julian calendar, the one that was developed by Julius Caesar, to the Gregorian calendar, which is a more astronomically correct calendar. It's got things tied up better. The Julian calendar, the date of spring, the first day of spring, kept drifting over the centuries, and to bring it back into line with when it had been long ago, they had to take 11 days out of the calendar, and Britain actually backdated, went back to some earlier dates and took 11 days out of their calendar as well. And one of the years that they took it out of was, or they went back to even before Newton was born. And that was why sometimes his birth date is seen as 1643, but it depends on which calendar you're using anyway. And he died in 1727. He's best known perhaps for developing the laws of motion and gravitation, at least in physics he is. He also did work in optics. He developed calculus. A lot of his scientific work was done in his 20s. He started college, and just about all he knew at the time was addition, subtraction, and he knew English, of course, and he knew Greek. And that was considered what a young man needed to have to go to college in those days. Many of the people just went to college to learn how to handle a business, and addition and subtraction were all you needed. By the time he finished college, 4 years later, he was about the top mathematician in Europe and one of the top scientists as well. But then he was expecting to just go to work at the college and spend the rest of his life there, but the college shut down for 2 years because of the plague. He went back to his stepfather's farm in Woolsthorpe, and apparently wasn't a lot of use as a farmhand, but he did get a lot of thinking done and started thinking about gravitation. That was when he mostly developed the law of gravitation and so forth. A lot of the work that he did, he just kind of kept it to himself. He didn't necessarily share it. People didn't know he'd developed the law of gravitation until sometime a couple of decades later. And Edmund Halley, you may have heard his last name before. Halley's Comet is named after him. He never saw Halley's Comet, but anyway, Halley predicted when it would return. But he and Robert Hooke had been trying to figure out if there was some sort of a force that was acting between the sun and the planets. And they didn't know for sure how that force might behave, but they'd been trying to do some mathematics with something they had in mind for a gravitational force. And Halley went to Newton and asked him, he said, Hooke and I have been wondering if there was a gravitational force that varied inversely with the square of the distance, what would the shape of the planet, or what would the shape of the orbits be? And Newton said, they'd be ellipses. And Halley said, well, how do you know? Newton said, well, I've proved it. And once this came to light, Halley got Newton to publish the research that he'd done in motion and all sorts of things. And a few years later, those finally got published. Halley actually paid for the publication of it. And that book that Newton published. It was called the Principia. You can still buy it. And it's the book that has Newton's laws of motion and gravitation and other researches that he did in there as well. And it's one of the great books of history, I think. Okay, Newton's first law of motion. This will be just about our last slide here. For the most part, it was developed by Galileo. And Galileo did research with things. I mentioned in class that at the time of Galileo, nearly everyone, accepted the science of Aristotle and thought it was absolutely correct. And something Aristotle had said was that it took a force to keep something moving. Aristotle also said it would take a force to get something moving, but he also said you have to keep exerting the force or the object will stop. And Galileo started experimenting with this idea. And he did things like, you could kind of imagine him going out on a village square in Italy somewhere and rolling a bocce ball on cobblestones, and it might not roll very far. Or rolling it on a lawn that wasn't very well trimmed, it would come to rest pretty quickly. But then Galileo worked in palaces sometimes, the Medici Palace and maybe other ones. You could imagine him rolling a smooth ball along the floor of one of those palaces and seeing how much farther it would roll than it did out when there was a rough surface. And Galileo was one of the first people who started doing thought experiments. And a thought experiment is one where you do the best job you can with actual experiments, and then you start imagining what would happen if I could do this perfectly. And Galileo thought, what if I had a perfectly round ball and a perfectly smooth surface? I think the ball would roll forever. And so he came up with something that was very similar to Newton's first law of motion. But here's a statement of Newton's first law. An object will remain in a state of rest or uniform motion unless it is acted on by an unbalanced outside force. Now, we need to decode this thing. What does uniform motion mean? Well, uniform motion is constant velocity. Okay, now remember, velocity is speed and direction. That means uniform motion is going to be something moving in a straight line without slowing down. Not a curve around the Earth or an orbit, but a straight line. Okay. Now, how about an unbalanced outside force? What does that mean? An unbalanced outside force, you can look at things all the time that have outside forces acting on them. Anything that's sitting on your tabletop. Your computer is probably sitting on a table or on your lap. If it's sitting on a table, the forces on it are balanced. One force that's acting on it is gravity, pulling downward on it toward the center of the Earth, but the tabletop is pushing up on it, balancing that force. And so the forces acting on it are balanced. But if you exert an external force that is not balanced, like you push on the side of your computer or anything else that's sitting on your table, you can change its state of motion. Now, it'll come to rest pretty quickly because there's friction between the tabletop and the object, but sometimes you can look at relatively friction-free situations. For instance, if you've ever played air hockey, there's a zillion little holes in the air hockey table that are puffing air out of them, and the little disc that you use in air hockey will float along on the cushion of air, and you can shove it across an air hockey table and it'll keep moving almost frictionless, almost without slowing down, till it hits the other side and bounces off and comes back. So that's about as close as you can get to not having any unbalanced outside forces on things, is something like an air hockey table. Now, we also need to talk about just what is a force anyway. It's a push or a pull. It's something that if it's acting alone can make an object change its velocity. In other words, it can make something accelerate. A few examples of Newton's first law. Don't see them acting perfectly, but you can see it acting pretty well a lot of times. For instance, let's suppose that we're going to look down on above from a car, and I'll just draw a rectangular car here, and there's the windshield there. And let's suppose that you've got a sunglasses case sitting on the dashboard, or it's up by the dashboard under the windshield. And your car is going forward like this, but you're in a parking lot and you have to turn to make a sharp turn. And when you do that, your car is now going to be here. Okay, the windshield is now going to be here, and something you might notice is that the sunglasses case can end up on that side of the car. Now, some people will say, oh, there's a centrifugal force acting on it. There is no such thing as a centrifugal force. That's a fictitious force we invent to explain motion like this. What's happening is your sunglasses case is demonstrating Newton's first law of motion. An object in motion will continue in motion with uniform motion unless acted on by an unbalanced outside force. Well, it just keeps going in a straight line. The car turns out from underneath it is what's happening, and it keeps going in its straight line. There wasn't enough friction between the dashboard and the sunglasses case, and so it slid across the dashboard there, although you could think of the dashboard as sliding out from underneath the glasses case if you want to. Another place this shows up is in the winter time. If you're driving on a road most of the time, if you make that turn, you're experiencing centripetal acceleration. It takes a centripetal force to produce a centripetal acceleration, and the force that acts on your car to let it make the turn has to be acting inward in the direction of the acceleration toward the center of the turn. But if that force isn't strong enough, like let's suppose on this road is a nice patch of ice right here, and your car comes along the road like this. If it's going to make the turn, it needs to have a force toward the interior, but if you're on ice, the ice has a maximum amount of force that it can provide, and it's easy to overcome that force if your car is going too fast. Remember, centripetal acceleration equals v squared over r. Well, centripetal force, well, we haven't talked about that. But anyway, the friction can't provide a force large enough to produce that acceleration, and so your car goes in a nice straight line and off into the ditch. So that's what happens. A simpler example, if your car is moving along a slick road in the wintertime, it will take a force. It does always takes a force to stop your car. That force is provided not by your brakes, that's an internal force, but by the friction between your tires and the road. And if that friction is diminished because it's an icy road, your car doesn't come to a stop as easily. It keeps going in a straight line for a longer period of time. There's still a little bit of friction, but it can be a tiny fraction of what it is on a dry road. So keep that in mind when you're talking about or thinking about driving in the wintertime. Remember Newton's first law. Another example, if you've got a bunch of books stacked on the seat next to you and you have to brake your car suddenly, those books will end up on the floor. There isn't enough friction between the books and the chair or between adjacent books to keep them stuck together or anything like that, and some of them will just end up on the floor. So Newton's first law shows up all over the place. One other example of Newton's first law, if you take something like, just have a ball on the end of a string, or just tie a string to just about anything, spin it around in a circle rapidly, and then let go. Okay, the string is what kept the object moving in a nice tight little circle, and when the tension in that string drops to zero, when you let go of it, your object will take off in a more or less straight line, although it'll quickly be acted on by gravity and come to Earth. But if you weren't on the Earth, if you were able to spin that thing far out in space, say halfway between here and the Andromeda Galaxy, you could let go of that thing and the object would take off in a straight line, and it would go in a straight line just about forever. So Newton's first law shows up all over the place. Now, one of the ideas that shows up in Newton's first law is the concept of something called inertia. And inertia is just the tendency of objects to keep doing, and I guess I spelled that right, odd spacing there, of objects to keep doing whatever they're doing. Now, we happen to put a number on this in physics, and we call it mass. But if you just think of this concept here, the tendency of objects to keep doing whatever they're doing. If they are at rest, they tend to stay at rest. If they're moving at some particular velocity, they tend to keep moving at whatever that velocity happens to be. And the more stuff there happens to be, the more inertia there will be. One example is, suppose you go to a grocery store and for once you get a good cart. Seems like a lot of times when you go to the grocery store you get a cart with square wheels, or one that makes this clanky noise as it rolls along. It's kind of embarrassing when you get one of those things. But you get a really good grocery cart. And here's a sketch of your grocery cart. And you have to just pretend you're pushing it along with groceries in it. And this is one where it starts up really easy, and once it's rolling, you can let go of the handle on it, and it'll roll all the way down the aisle. You have to run to stop it from running into other things at the end of the aisle or other customers. So it's a really good one. And it even works when you start loading it up. This is a day when you've had to buy a 50-pound bag of dog food and 4 of those 40-pound bags of salt for your water softener, and then a whole bunch of canned goods that were on the grocery list, and just all sorts of stuff. And so you've got a couple 100 pounds of groceries in there before too long. But still, it takes more of a push to get the cart moving, but once it's moving, it just keeps going and going and going down the aisle. So it's kind of amazing. And you'll have to run and catch up to it and exert a force on it to stop it. What you're experiencing in that case is the object's inertia, its tendency to keep doing whatever it's doing. If it's at rest, it takes a pretty big force to get that thing moving, but if it's moving, it takes just as big a force to stop it. And that's what you're experiencing. That's the idea of inertia. The resistance to changes in motion is another way of putting it. And it's not the weight of the load that you'd be struggling with in this case. The floor is supporting the weight of the cart. It's just the stuff that's in it, the inertia of the load. The number that we put on inertia, whoops, that's not a very good M, is mass, okay, a measure of inertia. And it's different from weight. Okay, we'll learn shortly about the difference between mass and weight. We talked about Newton's first law. They wouldn't bother numbering them if there was only one, and so we know there's going to be a second one, and that'll be Newton's second law. Newton's second law is this. If you've got some sort of an object and it's got a bunch of different forces acting on it, some of those forces may cancel out, but there might be a leftover force, and we would call that the net force acting on the object. It's the force that's left over after all the ones that cancel out are gone, or they've been canceled out. And Newton's second law is this: the acceleration of an object, and we'll use the letter A for acceleration, is equal to the net force acting on it divided by the mass of the object. And so we're going to have to be able to put a number on this mass in order to figure out what the acceleration is going to be. And the net force, you could have a bunch of different forces acting, but suppose you had something, a nice little cart sitting there on a tabletop, and it's got really good little wheels and it's almost frictionless. But there are still forces acting on this. For instance, the force of gravity is pulling it down, and we would call that force weight. Well, the tabletop happens to be pushing up on the wheels, but we'll just treat it as if it's acting at the center of this thing. This is the force of the table. And it's not the force on the table, it's the force the table is providing on the cart. Okay, so those two forces can be balanced. But then you can apply a force to this end of it, and that force won't be canceled out because this thing has really good wheels. And so this might be the net force, but we could call this the force of U, exerting a force on there. And when we add those forces together, the force of U plus the force of the table plus the force of the weight, those will be the net force. Now, these two cancel each other out, so it's really U that's providing the net force in this case. So that's what would happen. And the acceleration will depend on the strength of that net force divided by the mass. The more massive the object is, the smaller the acceleration is going to be. If this thing only weighs half a pound or something like that, it's not going to be very hard to accelerate. It doesn't have much mass. But if you start piling a bunch of lead weights on here, and the wheels still work pretty good with all those lead weights stacked on there, it's going to have more inertia and it will be harder to accelerate. So that's Newton's second law. Units here. Okay, often you see Newton's second law written this way. The net force is going to equal the mass times the acceleration. I'm not so crazy about writing it that way because a lot of people look at that and think, okay, you've got a mass and you give it an acceleration and that produces a force. That's not the way it works. You apply a force to an object and that's what produces the acceleration. And so keep that in mind. It's the force that produces the acceleration. But mathematically, this statement is equivalent to that one, but it's the acceleration that's the end result of the force acting on the mass. But we can figure out the units here. Our units of mass are going to be kilograms. And so those are the way that we measure mass in the metric system. In the American system, the unit of mass is a slug. And you don't hear that unit very often because we don't talk about science in the American system very often. And our units of acceleration are going to be meters per second squared. So the unit of force in the metric system is actually a kilogram meter per second squared. However, we use that combination of units so often that they get their own name. We call that combination of units a Newton. That combination of units gets called that. The abbreviation of a Newton, by the way, is a capital N. And in the metric system, when a unit is named after a person, when you write out the name of the unit, it's in lowercase, but the abbreviation is always in uppercase when it's named after a Newton. And there are a lot of different instances of that happening. There's a unit for magnetic field strength named after Nikola Tesla, and the unit is called a Tesla. The abbreviation for it is a capital T. The unit of charge is a Coulomb. The abbreviation for it is a capital C. But when you write out those units, they're always lowercase letters. So anyway, those are our units of force. The Newton. On Earth, if you talk about the gravitational force acting on something, if you pick something up and let go of it, it will accelerate toward the ground with an acceleration of 9.8 meters per second squared. The reason it does that is because of the weight of it, which is the force of the Earth pulling it down. And the weight of an object is equal to its mass times the acceleration it experiences when you don't have to worry about air resistance. And we usually ignore air resistance. And so weight is equal to mg. It's a combination of things. I'll show you why we don't use newtons when we're talking about weight. Countries that use the metric system will ask you how much you weigh, and they expect to be told in kilograms, but that's not weight, that's mass. They actually misuse the terminology. But, let's see. 1 kilogram on Earth, if you take it and multiply it by that 9.81 meters per second squared, or 9.8, we'll just use an approximation here, the weight of 1 kilogram, well, you can do this multiplication in your head. It's 9.8 kilogram meters per second squared. That's 9.8 newtons. And so, well, that's pretty easy to figure out there. 9.8 newtons happens to equal about 2.2 pounds. And these are only approximate. They're pretty close, but not exactly. And so this is the transfer from newtons to pounds, or vice versa. A person who weighs 150 pounds, and I'm using the abbreviation LB for pounds. Well, if I multiply that by 9.8 newtons per 1 pound, or 2.2 pounds, excuse me, I can find out how many newtons they weigh. So 150 times 9.8 divided by 2.2, and I get about 670 newtons. And that is their correct weight in the metric system. But nobody wants to weigh 670 of anything. And so you'd actually get your mass in kilograms instead and go by that, because it's not such a depressing number. Okay, this law does let you see all sorts of things. The larger the force acting on something, the bigger the acceleration is going to be. The bigger the mass is for a given force, the smaller the acceleration will be. And so if you can kind of understand that conceptually, it will be easiest to understand it. Newton's second law may seem kind of easy, but it can get complicated. There's a course that people who are studying to be engineers take. It's called statics. And in statics, you spend an entire quarter or semester studying situations where the acceleration is zero. That means the net force acting on something is zero. And it seems like, well, that wouldn't be very interesting, but the kind of situations they'll end up examining by the end of the quarter is a situation maybe something like this, where you've got some kind of a trestle bridge that goes over a valley or something like that. And I didn't draw it very good. These would all be the same size and everything, but let's suppose these parts of the trestle are this grid of steel girders that are all welded together, and they've got a hefty weight to them. They're all pretty heavy. They're sitting there on the earth, And then you have to build it so that it'll support the load of a train that's going across here. And you might do a calculation where, well, if there's a train going around here that's full of coal cars and it extends all the way across the bridge, and the coal cars weigh such and such a thing and such a thing, and the girders weigh so much and everything, what will be the force at this point in the bridge? Or how strong does this joint in the bridge have to be? And those are the kind of situations that they end up examining, and it can get pretty complicated. I used to teach that class, and this was before we used a projector and a nice computer for doing problems. We'd fill up in those days we already had whiteboards, but we'd fill up every whiteboard in the room with a problem, and we'd have to go back and erase part of the first whiteboard to finish the problem. So the problems can get complex. So Newton's second law looks fairly easy, but it can get complicated. So, but remember that. And we'll do some examples with this. I'm sure you'll do more examples, and they have examples in your textbook too. So check those out to get a good understanding of Newton's second law. I'll stop here. I plan on doing a Newton's third law exercise in classes in addition to the lab. So that's where we'll stop with this for tonight.